I said the first thing I showed was a neat solution because Joyent's already done that as cloud analytics. This has not been done in cloud analytics yet, so it's just some Perl programs that you go and run. So it's a manual step for further analysis. We've talked about, can we make it interactive? Can we make it real time so that the user can log in and click and have it come up? Probably. It doesn't look too computationally expensive. It may not be every single second, but it's something that we're looking at. We don't think it's going to be too difficult to solve. It is a lot of data. We know it's a lot of data that's processing, but it's just a lot of text data to rip up and spit out. So, nice idea. Code's out there. Flame graphs were born out of necessity on cloud environments. Perf issues need quick resolution. You've just got hack and used. I've had that to a bunch of customers. And then suddenly they have a lot of traffic, and things are starting to hit hot CPU, and they want to know if there's some quick tuning to alleviate performance issues. Also, because everyone's running different versions of everything. When I used to work at Sun, I could have rolled a tool like this, but I was so familiar with the stack traces and the versions of software I kept looking at inside the kernel and inside user land that I often was able to eyeball it from the output. Now there's just too much data. Customers are hitting issues too frequently, different versions, and I need to remind myself, it's like, is this that issue I've seen before that has a particular spin lock? It's just a data problem. So, data can be available, just to summarize that particular example. For cloud computing, it's easy for operators to fetch on OS virtualized environments. Otherwise, it's agent-driven. You have to log in. If you are doing profiling that's agent-driven in cloud computing environments, there might be other issues, depending on how the profiler works, whether it's got access to the CPU instrumentation counters and can do interrupts based on them. So there may be some difficulties. I just used a new visualization just to make it easier to process that data quickly. So, it's a fairly neat solution to the problem. The next example problem I want to go through is CPU latency, still on CPU. Now things start to get a bit worse. CPU dispatcher queue latency is where a thread is ready to run and waiting its turn. It is observable in coarse ways. VMstats R column, which is the ready to run. On some operating systems, that's really not updated that often, so it's updated once a second. So you go and look at the clock routine in the kernel. I've been meaning to fix that for a while. High load averages is actually, at least on SmartOS, that's actually a much better way of providing an idea of the CPU dispatch queue latency, which I would term as a saturation metric. The load averages, at least on SmartOS, are calculated using CPU microstate counting. A finer way to understand it, although this time I think only SmartOS and Lumos-based systems have it, it's PRStat minus ML's latency column. So that uses thread microstate counting, which was invented on Solaris, and it's really cool because you can actually see the percent of time each thread spent waiting on the dispatcher queue. However, even though I can identify this, it's still a leap to go from that to saying how much was that hurting an application. So my customer has MySQL slow queries. We know the CPUs are very busy, they're kind of saturated. What percentage of time for that slow query was CPU dispatcher queue latency? And even PRStat minus ML's latency column won't answer that. Since Dtrace can look inside the kernel, Dtrace is dynamic tracing, we can look at the scheduler events and do our own calculations. And so a script that I'll use occasionally is zone dispatch queue latency.d. It's printing out a distribution plot showing the dispatch queue latency in nanoseconds. It's a work in progress. This is where things aren't that nice to do. To start with, there's a lot of overhead. There can be a lot of overhead to do this. Scheduler events are very frequent. I'm tracing scheduler NQ and DQ events. I'm saving a timestamp in an associative array, and I'm retrieving it on DQ to do a delta. And that can add up to overhead. And there was some other weirdness with this, maybe missing a code path like thread migrations, or maybe just an artifact of the scalabilities. Kind of works enough to solve issues, help customers understand the impact of dispatch queue latency on their applications. And of course I can rewrite this and include higher level application details as part of that. So I may need to express this as a component of a MySQL query or as an Apache request or something like that. Instead of zone name, I could be putting out process name or anything else. Tracing, scheduling, queue, DQ events, as I said, cost overhead. I would prefer only to trace DQ and reuse existing microstate accounting timestamps. As it turns out, the kernel is already saving timestamps when threads are enqueued, and then it reads those timestamps when threads are dequeued and dispatched. That's how the microstate accounting works. There's just a problem with the type of timestamp. One is scaled and one is unscaled, and I haven't figured out a way in Dtrace to translate one to the other. If I solve that problem, I can actually do that in a much less overhead way because I just detrace one event, don't have to save data. On the cloud, things get even more complicated. Instead of just the regular CPU dispatcher queue latency, if you have operating system virtualization, you can have latency that's not visible in VMstats R, and it's because you've hit quotas and you're being throttled by the operating system, and you can have high CPU latency even though there are idle CPUs on the system. So things get actually pretty weird. So customers are looking at they think they can understand the dispatch queue latency, and yet CPUs look idle. It is visible as part of PRStat's latency column. We've been adding kernel statistics to try and get better visibility on this. So one of them was insect wait RQ for the nanoseconds in the wait run queue state per zone, so that each tenant in cloud computing can have at least some way of understanding and plot that second by second of the amount of time my threads were waiting. Hardware virtualization has some issues. That's why you've got VMstats ST for stolen, so you see time that I didn't have available. And if it is a OS virtualized environment, and you've got something like Dtrace, you can just go into the kernel and then trace the events that are doing the resource controls. So I can write, this script's actually easier than the previous one. This one's looking at the CPU cap latency that's enforced to throttle tenants and prints out graphs for long. So that's kind of tricky, and there's not a really nice solution to this. Dtrace is, like I said, it's work in progress. There's some overhead. I just want to put this data out there. Partial data is available to understand CPU latency. New tools and metrics were created. As I said, the Dtrace solutions do have overhead, but we should be able to improve that. Hopefully some new case stats will be sufficient in the meantime. I have 3 examples for CPU, 1 example for memory. This is one that I spent all week on. It's a React database which had endless memory growth. It was expected to hit 9 gigabytes, but after 2 days, it was hitting 40 gigabytes and more. This was a performance issue because it eventually exhausted the available memory, and it was doing paging and terrible performance, and the customer needed to restart the database. Is it a memory leak? People often say memory leaks, but they actually mean application growth. Memory leak means something very specific. If you're a programmer, it means you've lost memory and there's no references to it. And when I see things like this, I generally think it's an application growth. Application's doing something dumb. It's not actually a memory leak. This one was Voxa. Voxa is a company that does a phone app that turns your phone into a walkie-talkie. It's really cool. They're on CNN recently, and they've got lots and lots of users doing all sorts of innovative things. And they're also driving a lot of load to Joyent. They're using React, and it sits on top of Erlang, VM, and of course they're running on SmartOS. And given this memory growth was actually a real pain that they had to restart the Reacts every couple of days, we had a chat room where all the teams were involved. So we had the Voxa team, we had the Basho team, we had people with Ericsson experience, and the Joyent team, myself, and we're all trying to figure out where is the problem. And my presumption would be application growth. That's what I've seen, it's my experience, that's what I've seen a lot before. I wouldn't really expect it to be a memory leak. some of those teams were already blaming the operating system, saying it's an operating system memory leak. Which made me smile as well. It's like, yes, it's unlikely to be the operating system. It's, based on my experience, it's more likely to be everything else. I mean, it's going from 9 gigabytes to 40 gigabytes in 2 days. Like, operating system's been around for a while. SmartOS is based on Lumos, which is based on Solaris. It's an enterprise operating system. There's a lot of banks and heavyweight enterprises running this forever. Same code, so I don't think it's the operating system. So, looking at the other layers. This, by the way, is important to mention, and as part of the performance methodology, the first step for a lot of these issues, the first step is to find out, do you have an issue in the first place, or do you think you have an issue? We know we have an issue because it's growing in the new page and then performance is bad. Second step is which team is responsible for the issue so the other teams can go home. So having us all work late nights all together and this is a very friendly environment, we're not blaming each other, we're just trying to figure out which area it belongs in, does waste people's time, so we really want good observability. Heap profiling is kind of hard. So there are some tools out there, but this is a production React database, and we can't really run it with heavyweight instrumentation. So what is in the heap? And if you use tools like PMAP or whatever to look at the process address space, there's lots and lots of gigabytes in the heap. Why does it keep growing? We would like to answer this in production without restarting the apps. Some experimentation was tried, like setting the backend allocator to mmap, using other allocators, on the assumption that it was the operating system without success.
Did you use the Google PerfTools allocator?
The Google PerfTools allocator looked at, didn't use that. That looks like it's for, yeah. I'm unsure if that would work. I mean, this is a very performance critical environment, and so one of the top priorities is what is the overhead of those allocators. The allocator we weren't using was libumem, and this is kind of the reason we didn't go and use Google PerfTools. Libumem was actually picked because of a thread locking issue, but libumem, which is a userland slab allocator, already comes with a lot of performance observability, similar to what the Google PerfTools does. In fact, both of them are similar in many ways. Just a bit of background, libumem was written by Jeff Bonwick and Jonathan Adams. Jeff Bonwick invented slab-based allocation, which I believe has ended up in Linux and everywhere. That's how the kernel, the Solaris kernel does allocation, slab-based allocator. It's good for performance, it can do per CPU caching. So we were already using libumem. Libumem had been designed so the detailed observability was available, allowing heap profiling and leak detection. And it was designed with speed and production use in mind, although it still comes with some cost. If you want to turn on the full umem debug equals orders, so you get stack traces and get memory logs, you are going to spend many megabytes saving that stuff in memory, and you're going to spend some CPU cycles. They actually turned it on for a system, and since there was a lot of CPU headroom, it actually didn't go so bad. And so it was able to actually capture some really interesting core dumps of the process. And run, libumem also provides find leaks. Find leaks is its leak detection software, which does a garbage collect run, a conservative garbage collect run, and will tell you what's been leaking. And with umem debug ordered on, you get stack traces and all the goodness. It wasn't a memory leak. So it wasn't a memory leak, it was still growing. libumem does provide some other observability. A lot of this stuff wasn't documented very well. Well, it was documented in the code and it was documented in the bug, but umem malloc info actually shows the slabs, and we can look at how much is malloc or in use and the overhead of the slabs. vmem showed us the hierarchy of segments, and this is what was most interesting, where the total for the S-break top, the top of the heap, was 14 gigabytes. This particular capture was at the 14 gigabyte state, whereas the in-use was 9 gigabytes.